Hi, Christina.
Hello.
Still got plenty of time, at least 5 minutes or so if you have any questions. Ugh. Looks like you're the only early bird this time, Christina.
I almost forgot we had class today.
Yeah, it's such a pretty day. It feels like summer. Just go ahead and finish the semester and run.
That sounds good to me.
Oh, we have another one. And another. Now people are coming. We still got about another minute. If anybody has any questions, you can ask them before class starts. Treat it like an office hour. Got another student. Oh, two more students. All right, now it's time for class to start. I only got 6 of you in here, though. That's kind of a little depressing in terms of the number of students, but I'm sure they'll show up a little later. Again, I'll ask one more time. Does anybody have any questions about any past material? Hopefully you've maybe at least watched the end of last time's session where I haphazardly had forgot to remind you last time about the redo of the final. Excuse me, of the midterm. So as I said, then you had the opportunity to completely redo the midterm. I left the actual midterm open with the not only the multiple choice available for you to see, but actually the right answers for you to see. And I asked that you look them over and record them so that you could rework in its entirety the midterm. And you're going to turn that in a week from yesterday. No, a week from yesterday. You're going to turn those in for some number of points, up to some number of points on your actual midterm grade. Also, one of the things I plan on doing, no matter what happens with that, and basically I'm going to stagger the number of points you can earn, like those people that may have scored in the 20s or 30s or something like that. Maybe I'll give them the chance to get 30 or 40 points, whereas the people that scored in the 30s, excuse me, in like the 50s or 60s, maybe they only get 20 points, up to 20 points. And then anybody higher than that probably only going to get 10 points. But and of course you don't have to do it at all. But if you get 100, you'll get all the points that you have based on the original grade you got. But if you get a 50, then you're only going to get 50% or whatever, so on and so forth. However, if at the end of the semester you take another proctored exam, which is the final, and if that final exam grade is better than your midterm, I will replace your midterm grade with that. Okay, because really the midterm is really my attempt at showing you the difference between taking an online test in which you're allowed to do Google searches, have your notes, have your book open and all that good stuff. And that's completely legal on your online test versus a test where you actually have to do the work without having resources like books. The only thing you're allowed to have is an equation sheet and maybe some constants. So sometimes students don't really understand how little they're learning by looking up stuff. So that midterm is often the first chance you get to actually see how well you are or are not learning. So I normally make it such that if you do badly on the midterm, I will replace the midterm grade with the final exam grade because it gives you that other chance. Not only that, I'm pretty open to the idea that basically, hey, you might screw up a little bit throughout the semester, get behind, but the day of reckoning is the final exam day. So if you can pull your stuff together on that day and do really, really well, I might just throw away your class average and give you a grade that is impossible to get based on your class average. But only in a way that improves your score. Obviously, I can't do anything more negative than the syllabus says. But for instance, if you score a 98 or a 97 or something on the midterm, it's a really high A. Going into, or excuse me, on the final exam, that's a really high A on the final exam. If going into it, you had some grade that was so low that you could only get a C, and that was if you got a perfect 100. If I look and see that your grade comes up like that, but you scored a 97 or 98 or something on the final, I'm definitely not letting you take that C. Bare minimum, I'm going to bump you up to a B, but I might even give you an A. Again, this all depends on, things like when I go back and look at your monitor, your respondus monitor, if I see any fishy behavior, then I'm probably not going to do it. And that means if I see one person with fishy behavior, I'm not going to do it for anybody, because if I do it for one person, I got to do it for everybody. And if I just see one that's not conclusive of someone cheating, then I'm not inclined to give them that break. But at the same time, I have to sort of stick to that for everybody. So anyways, that's just another little note on there. I did make a place in this week's module where you can turn in that work. You have to write it out neatly. You have to write out the actual question, or you can what I recommended is you take screenshots of the actual test with the right answers, and you just post those, like say in a Word document, turn the margins down to 0 or something like that. Post the first question, cut out of it anyways, into the Word document. Then solve the problem on a piece of paper, take a photograph of that, insert that right below the question, neatly written, the answer clearly indicated with a box around it, that sort of thing. And then insert question number 2 with the answer choices, and then solution number 2, and so on and so forth. And then save that Word document as a PDF and turn that PDF in. I only accept PDFs, so that's what's going to happen if you do wish to turn that in, and it should be turned in by 11:59 on Wednesday of next week. So, anybody have any questions on that? All right, well, that was something I completely forgot to tell you. Yes, ma'am, Christina?
I missed the first part.
Oh,
I heard turning into a PDF. I missed the first 2 minutes of the conversation.
Okay, so I sent you an email out Wednesday night as well. Or excuse me, you guys meet on Tuesday. On Tuesday night as well, I sent you an email about this. And what I just said was also completely in the end of the video from Tuesday night. So you can also catch it there. But what I was saying was you have a chance to improve your midterm exam grade by completely redoing the whole thing, not just the parts you got wrong. You got to do the whole thing. There's explanations in the module where you turn it in on this week's Canvas module. You'll see test redo, I think is what it's called, or midterm redo, and it tells you exactly what you have to do, but it has to come in a PDF form. I have to have question with question choices verbatim. You can insert actual photos. That would save you some typing, or you can handwrite it in, or you can type it in, whatever you want to do. But then immediately below question 1, you're going to do your handwritten answer 1, written on paper, say neatly with the final answer circled, and then take a photograph of that, insert that right below the question, then put question 2, so on and so forth, ultimately saving the whole thing as a PDF and turn that in as a PDF. And someone's raising their hand, so question, that would be Michael.
If we do worse on it than we did on the midterm, it won't affect us, right?
No, it's only going to improve your score. So if you got like a 12 on it, it's going to be 12% of, let's say, 20 points. If you happen to be in a test range that gets 20 points, it'll be 12% of 20 points just added to your grade. So it's just helpful. What I really want y'all to take this as is not an opportunity to improve your midterm grade, which it will do. I want you to take this as an opportunity for you to actually learn how to solve those problems. I would much rather you do horribly on the one you turn in to me and therefore get hardly no points, but having learned how to solve several of the problems that were on the midterm, because that's what the purpose of this thing is completely for the opportunity of you to learn how to solve these problems from chapters 1 through 20, or excuse me, 21 through 28. So yeah, it only improves. And the other thing I said from Mata, by the way, was that the midterm grade, if that's lower than your final exam grade, I will erase your final exam grade and give you your midterm. I will erase your midterm grade and give you your final exam grade for it. Not the other way around, but just that. Did that answer everything you had for me, Famata?
Yes, sir. Thank you.
You're welcome. All right, so we have a couple issues left. I sort of wrote down the transformer equation last time, made arguments about why it came into be. I'm going to do that again, mainly because I don't memorize the transformer equation, to be honest with you. I understand the concepts well enough that I put it together, more or less derive it each time I have to use it. I just, from a young age, I was a little scared of Alzheimer's. So I've been building my whole life around forgetting everything, which is kind of weird, but anyways, that's what I do. But it sort of helped because I seem to understand physics a little better than a lot of students that were in my classes with me at the time. So maybe that was the dividend it paid. So let's start off with that, and then I'm going to solve a really good problem regarding transformers. And then I'm going to solve a problem where we can see that, in fact, the electric field sort of behaves like the magnetic field in Ampere's law. And in fact, that Faraday's law is in fact identical in form, at least half of it is identical in form to Ampere's law, where you just replace the magnetic field with the electric field. So we're going to work that problem as well. So let's see if I can get started without falling asleep in real time, because I don't know what's going on again. I'm yawning again. I had a great night's sleep. I don't know why I'm yawning right now. All right, so I'm going to go ahead and share my screen. Feel free to ask me questions. You can just blurt them out just in case I'm not looking at the chat. Feel free to blurt them out. If it gets too noisy, I'll ask everybody to go back to, raising their hand or whatever. But until then, just blurt it out when you have a question, or just say, excuse me, Mr. Younger, I have a question, and that'll be fine. And I want you guys to ask me questions. I don't know if you know this, but that's how I get the big money that I make, is by supposedly teaching you guys. So that's how you see this rich man before you. All right. So first off, I want to tell you that if you look at Faraday's law, it basically says the EMF induced. Now, you normally use E. I'm going to go ahead and just use V for right now, just because everybody should know by now that electromotive force is just the old-timey word for what we now call voltage. And it's actually equal to negative, and we'll leave a space here. You'll remember what the space is for, hopefully already, but if not, you will in a second. It's the derivative of the magnetic flux with respect to time. So I write that capital phi, and that capital phi with a subscript B means flux. And of course, we remember that the magnetic flux in its most general form is that capital phi sub B, or phi sub B, and that's equal to the integral of B dot dA, because in fact, it's the flux through a surface. And the surface doesn't necessarily have to be flat. It can have all sorts of curves and stuff like that. And the magnetic field doesn't have to be uniform. So the magnetic field can make all sorts of angles. So by dicing it up in infinitesimal little area segments that are, infinitesimally wide by infinitesimally long, we get an area 1 that looks sort of flat, and 2 is so small that the B doesn't vary very much over it. And then we just take the dot product of that little area with that B at that particular section, and then go on to the next one and sum them all up. So that's how the flux comes in. Now, the part that I left the blank for is because that we know that you can increase that voltage by increasing the number of turns. So if you have a magnetic flux that's changing in time through a circular loop of wire, then you'll get a voltage. But if instead of having a circular loop of wire, you have a coil of loops of wire that are essentially the same size as the single loop of wire, only there's, N loops, then you get N times as much voltage. Okay. So in general, what we see is that V over N in magnitude. So I'm just going to write over here magnitude. In other words, let's ignore that. Ooh, I don't know why I wrote a B there. I guess I was thinking of some word with a B in it. Magnitude. In other words, let's ignore that negative, as I've told you before. Unless you're putting this equation into another equation, a lot of times we just drop the negative in Faraday's law just because we're really trying to figure out the magnitude of the induced EMF or the magnitude of the current. And the negative just changes sort of in some sense of direction. And a lot of people see it as if it's the reminder for Lenz's law. So for just a magnitude, what we see is that the voltage divided by the number of turns is actually equal to the change in flux with respect to time. Okay. So if we're able to design some object that can hold the magnetic field from a given coil of charge, a coil of wire, for instance. So in other words, we could have a coil of wire, let's say like this. And that coil of wire could be very neatly packed, nice and neat or whatever, like a solenoid is, or it might be crap. The main thing is that it will have a magnetic field going through it based on the direction of the current going through it. And that magnetic field usually is pretty uniform. Well, if I now took, say, another coil of wire, and let's make this one say blue, a different color blue, in other words. We had another coil of wire like that. What would happen is some of this magnetic field lines from the green coil would enter the blue coil, the dark blue coil, and that would have a flux as well. Well, as you might suspect, the magnetic field coming out of that green coil is going to rapidly diverge and go off, in fact, like this way, and this way, and this way. So you're likely to not get very much. But what we've discovered in physics by experimentation of Faraday and various people in the 1800s and 1700s was that you can actually hold that magnetic field lines a little stronger and keep them from deviating out by putting a ferromagnetic material through the center of the solenoid. So if I actually stuck, for instance, a iron rod down the middle of the green solenoid, then that iron rod might stretch the magnetic field to go just a little bit further beyond the end of the solenoid before it starts to loop back up on itself. Because remember, all magnetic field lines, at least in the long term, make a complete loop and come back around like this. So they've still got to break away, because that equivalent of Gauss's law for the magnetic field, del dot B, is still zero. So there's no such thing as a magnetic monopole, which means all these magnetic field lines have to be closed loops. But still, we can stretch it out just by putting an iron core through there. So one of the ways we found that that's particularly or one of the ways that we found has been a particularly effective way of doing that is we take and make a little iron loop, if you will. Let's say the little iron loop looks like this. So it's sort of, I normally tell my students it's like a pilgrim belt buckle. So if you remember the belt buckles that you wore as a kid in, say, the little Thanksgiving pageant or whatever that you had in grade school, it was almost always that students had a little belt buckle like this, if you went to school in America anyways. So if you actually made that out of iron, it turns out I can then take, for instance, I can take a loop of wire, wrap it around here, and I can wrap it around, thousands of times if I want to. And in fact, there's some advantage to putting more of them around. But the main thing is, I'm going to have this wire come in carrying a voltage VP, and the number of turns on the side is going to be N sub P. Now, this iron will actually cause the magnetic field lines to behave a little more usefully. In other words, they'll go around like this instead of just shooting out and then coming back in the other side. They'll mostly go this way. You are going to lose some, but it turns out efficiency on modern day transformers is very near, say, 99% or actually above 99%. So if I can use that iron loop like that to carry the magnetic field lines around, then in principle, I can come back and put another loop of wire on this side. And I'm trying to show a lot more on this side. And in this case, I'll have N sub S coils, whereas the other side, I had N sub P. Now, for the record, what the P and the S are, the P is for primary and the S is for secondary. And the nomenclature that we use is if NS is greater than NP, then this is called a step up transformer. And that means it steps the voltage up. So again, if it's pretty efficient, then basically the same flux that goes through NP is going to go through NS. So we can say, well, that means roughly speaking, d phi primary over dt is equal to d phi secondary over dt. And of course, this means, based on the magnitude equation I put up above, that means that v primary, whoa, started writing an n instead of a v. That means that v primary divided by n primary is going to equal v secondary over n secondary. Oh, excuse me. Yeah, that's right. Okay, so that is a version of the transformer equation. So we can box that off if you want. And of course, it's an equation that you can use on your equation sheet, but you might want to solve it, say, for v secondary. And I might want to cross my T down here since I just didn't do that. But anyways, what I'm going to say is if I solve this for v secondary, what I get is v secondary is equal to n secondary over n primary times v primary. And you can see now why it would be called a step-up transformer, because if NS is greater than NP, then you can see NS divided by NP is a number greater than 1. And that means, in fact, that the secondary voltage is greater than the primary. So I will put that note right here. V secondary is greater than V primary. And that's why we call it a step-up transformer. Does that make sense? So that is the derivation that I told you, because I never remember, you know, when I put them on V's on one side and N's on the other side, I can never remember whether it's the voltages that have the subscripts aligning or if it's the currents that have the subscript aligning. So I just derive it every time. Now, let me show you the ambiguity that comes in that makes me have to do that, because there's an equation for what happens to the current as well. And basically, if it's 100% efficient, then P primary is equal to P secondary. That's the power. And what that means is specifically I primary times V primary is equal to I secondary times V secondary. Now, we know the efficiency is actually more like 99%. Okay, so that means probably the I secondary times V secondary is about 0.99 of the I primary times V primary. That's okay, no big deal. We just know roughly what it's going to do. And basically what they do is they wrap it and then they, you know, measure the voltage they put in, measure the voltage that comes out, and then they stamp it as a such and such transformer that, you know, lifts it by some fraction. And then you just know that based on their own experiments. So with that in mind, what you see is that IS over IP, whoa, it keeps turning into an eraser. That's really aggravating. Okay, so what this means is that IS over IP is in fact equal to IS over IP means the IS comes over on the bottom, and that gives me VS. Whoa. That gives me VS over VP. But if we look at the transformer equation we already found, we know that VS over VP, wait a second, is that right? IP, VP. Ooh, I did that backwards.
I think it's switched.
Yeah, thank you. I'm glad you caught that. I was just looking at it and saying, this isn't coming out right. Yes, IS over IP, I was actually trying to do it the other way. So IS over IP is actually VP over VS. Dang it, come back here. VP over VS, thank you. Now, if I look at VP over VS, I think you can see that's going to be NP over NS. So now we've got another transformer equation that basically says IS is equal to NP over NS times IP. So what that tells you is, remember that step-up transformer is when NS is greater than NP. Well, if NS is greater than NP, then NP over NS is actually going to be less than 1. So you see that for a step-up transformer, it actually reduces the current going through. Okay. Now, the whole reason me bringing this up is basically the fact that we have high voltage power lines going across country fields all the time. And they basically supply power from power plants, which, you know, make on the order of gigawatts of power and stuff like that. And then they send that power out over these power lines to substations. And then substations are places where not only can they step the voltage back down, because it turns out the best way, the most efficient way to send that power, you know, large distances over the country is by using high voltage. And by using the high voltage, it's no longer that useful for a home. So when it gets to a neighborhood, you have to have things that can bring it back down to a lower voltage. And it's fairly typical that the lines connecting to individual houses just before they connect to the house will normally be like 15,500 volts. And what they have to do to make that go into your house is then they have a small transformer like up on the telephone pole, or maybe they'll have a transformer station outside of a neighborhood, and that'll bring it down to some lower value. And then you'll have another transformer that brings it down the rest of the way, because what comes into your house is basically triphasic. That means 3 different phases of AC voltage at 120 volts, root mean squared. So we have to bring it down from whatever that is on the power lines at our poles or under the ground. We have to bring it down from that, which might be 15,500 to 120. And the way we do that, of course, is with a step down transformer. So I'm going to first show you exactly why we use a step down transformer and a step up transformer, and show you why it's so efficient. So let's consider an example. Consider a power plant producing 30 kilovolts. And now we're going to supply this for 10,000 houses. And it turns out that 10,000 houses would require 2 million amps. Because it turns out, like I said, each house uses about 200 amps. So for instance, when you buy a house or you build a house, the power company automatically will come out. I mean, after you have to, your builder calls them, or the electrician that does the electricity part of your house will call them, and they'll set up someone to put in what they call a service entrance. And that service entrance is basically a power supply coming from either the telephone poles or underground down the road. It'll come to a side of your house where there will be a circuit panel on the opposite side of the wall, and they'll just run the power in there. And then an electrician has to connect most of the circuit panel, which is where you'd have your circuit breakers, or used to have fuses. But that service brings in 200 amps. Now, if you need more power, the power company will gladly sell you more. It's just most people don't need more than 200 amps. In fact, a typical house uses about 30,000 watts per day. So that can give you a rough estimate. So we're really fixed on the total number of amps that we have to supply. And the power plant tries to make as high voltage as it can within reasonableness. You know, you get to a certain high voltage, the voltage is so high, it's just really hard to deal with in a safe way. So for instance, a lot of the electricity that we used in atomic physics when I was an undergraduate and a graduate student was, bare minimum 50, 60, 70,000 or 100,000 volts. And with that type of scenario, all your equipment that handles it has to be normally caged off with a big aluminum cage. And you actually take long pieces of lucite or plexiglass to go through the holes in the cage to reach out with a little suction cup looking thing that touches the knob and turn it. Because if I actually walk in there, the voltage is so high that it will cause the air to become a conductor and send current right through my body to the ground and kill me. So obviously there's some negative aspects of the power company making too large of a voltage because there's just, it's a forbidden region and a large amount of forbidden region that have to be there. So it turns out most of them make and deliver power at 30,000 volts or 30 kilovolts. So we consider a power plant producing 30 kilovolts and 2 million amps. That is several miles from the neighborhoods it supplies. Because of that distance, R is equal to, on the order of, let's say, 10.0 ohms. So these are pretty good sized wires. In fact, you can't make but so big a wire. You actually have to have braided wire, but ultimately the radius or the diameter of the wire could be like 2 inches or something like that. So with that large of an opening, you actually get a fairly low resistance where literally miles might only be about 10 ohms completely for just wire. And they mostly use like aluminum for going large distances because aluminum is a lot cheaper than copper and is only moderately less conductive than copper. So they do use aluminum a lot. With that in mind, what we're going to do is calculate the power loss. So A, what is the power loss? And B, what if we sent, let's say 1.20 times 10 to the 6 volts. In other words, what I'm going to do is first I'm going to assume that we just took the power as it is at 30 kilovolts and 200,000 amps, or excuse me, 2 million amps, and calculate power from that to figure out how much actual power is just wasted in heat. And then in the second part, we're going to say, okay, I'm going to use a step-up transformer, and the step-up transformer is going to step the voltage up from 30 kilovolts to 100 or 1.2 million volts. And obviously that's going to bring down the current because whenever voltage is stepped up, current is stepped down by the same fraction. And we're going to see the power that's wasted in that way. Now, in both cases, we're going to use P equals I squared R, not because I'm trying to fudge the numbers, but because you might not realize it, but that 30,000 volts has nothing to do with the power that's lost. The power that's lost when I send, say 2 million amps across a 10 ohm wire is actually that 2 million amps times the voltage drop across that, several miles of 10 ohm resistance. Okay, so we'd have to actually calculate another thing, whereas I can use I squared R and I already have the current and I have the resistance. So that's what we're going to use. So let's say I switch to red for the solution. And I don't know why I just made a capital L. It might be that, I don't know, I'm a homicidal maniac, but it just drives me crazy that I just did that. So we said power is equal to I squared R. Now that's the same thing as P equals IV. It's just we then plugged in V equals IR, Ohm's law, in other words, and got I squared R. So that's where that came from. So part A, we're going to see the power lost is going to be 2.00 times 10 to the 6 amps squared times 10.0 ohms. And with that, I think you can see this is going to be a buttload of electricity, buttload of watts, in other words. 2 e to the 6 squared is 4 times 10 to the 12th times 10. That's 4 times 10 to the 13th. And that's actually watts. That's joules per second. And remember, a joule is about as much energy as it takes to lift a really good, juicy, red, delicious apple from the ground to a kitchen table. So if we're talking about 4 times 10 to the 13 watts, we're talking about enough energy every second to lift 40 billion. 10 to the 9th is billion, 40 trillion. Okay, 40 trillion red delicious apples to the height of a table every second. Okay, so that's a pretty big loss. And if I remember correctly, it's only like 10 to the 12th joules is what the US uses per year. I may be misremembering that, but for some reason that number sticks in my head. Feel free to correct me on it if you have a Google machine. Okay. All right, here goes part B. So part B, what I'm going to do is I'm going to use V secondary is going to be equal to 1.20 times 10 to the 6 volts. V primary is, of course, 3.00 times 10 to the 4th volts. So I can find NS over NP is equal to question mark, because I know VS over VP is equal to NS over NP. So taking 1.2 times 10 to the 6 and dividing them by 3 times 10 to the 4th, gives me NS over NP is equal to, make sure these decimals show up on here. So 1.2 e to the 6th divided by 3 e to the 4th gives me 40. So I really only need to increase the voltage by about a factor of 40. Okay, so I'm going to call that 40.0 because obviously I use 3 sig figs everywhere, so that should work. Now, because of that, I can also say that the current is going to change as well. So I secondary is actually going to be N primary over N secondary times I primary, which is actually the same thing as 1 over N secondary over N primary times IP. And I just put it that way because that's basically what I know as NS over NP. So I secondary, when I do this, is going to be equal to 1 over 40 times, we said it had to come out with 2 million amps. Yes, 2 million amps. So the primary was 2 million. And the secondary amps are now going to be 2 e to the 6 divided by 40. That gives me 50,000. And that's 50, yeah, that is 50,000 amps. So now P lost, which is I squared R again, in this case is going to be 5.00 times 10 to the 4th squared times 10.0 ohms And that's going to be 5e to the 4th squared times 10. And that's going to give me 2.5 times 10 to the 10th. Watts. So instead of losing 10 to the 13th, 4 times 10 to the 13th, we're going to lose 2.5 times 10 to the 10th. That actually means a percent difference or a percent change equal to, we had 4.00. Actually, it should be final minus initial. So I'm going to do 2.50 times 10 to the 10th minus 4.00 times 10 to the 13th divided by the original, which was 4.00 times 10 to the 13th. And then I'm going to move the decimal 2 places to the right by multiplying by 100. And that should give me 2.5 e to the 10th minus 4 e to the 13th divided by 4 e to the 13th gives me negative 99.94%. So basically we saved essentially what, the whole amount, 99.4%. So in other words, it's basically cut down to well under a half, obviously. Anybody have any questions on that? Now, of course, what we have to do with this power, once it actually gets there, is we got to step it from the 1.2 million to a more reasonable amount of power, or at least a more reasonable amount of voltage. As I told you, when voltages are so high, they're quite easily able to ionize the air so that electricity will be conducted through what's otherwise an insulator. For instance, I used to run in a gated community in Chapel Hill called Governor's Club. It's like where, for instance, Eric Montross and a couple other guys, I think Jerry Stackhouse owned a house there. Dean Smith for Carolina used to play basketball there, I used to play golf there, as did Michael Jordan, stuff like that. So it's kind of a cool little neighborhood or whatever, but it's literally on a mountain. And there's one part, it's called the poor section, which is a place back in the 90s where the houses were only, $600,000 or $700,000 instead of the $2, $3, $4, $10 million homes. So people sort of haphazardly called it the poor section. But anyways, you get up to the top of the hill and those power lines that normally are hundreds and hundreds of feet over, obviously they're not quite that same level of voltage. They're nowhere near the 1.2 million volts, but from my estimations, they're at least 30, 40,000 volts, because when I would run under them, I could hear the ground and the air popping and ionizing around it. And if it rained, it got really bad. Like I could feel it. My hairs on my arms would stand up. And back then I actually had hair on my head too, though, so that would stand up. So yeah, there is a downside that we got to remember, that the higher the voltage is, it offers little or no protection, air does. So for instance, I remember someone building a house on Old Battlefield Boulevard. So when you're coming from North Carolina into Virginia, you cross the state line, and Battlefield used to go to the left there. But now they got the expressway that you just go straight on. If you go left there instead, you'll run by Hickory High School and that sort of thing. But just before you get to Hickory High School, there were some houses being built, and the power lines are, a good 15 feet off the ground there. But the problem was some of the trucks that they would bring in to carry roofing stuff and trusses and stuff like that for the house, they would be quite tall, so they need to get under there. And obviously, a big metal truck touching a power line is not that safe, because what I'm telling you is the voltages that they run alongside of the road are usually like 15,500 volts, something like that. That kind of voltage is not small enough so that the rubber housing around the wire would actually protect you from getting electrocuted. So that would be a problem. It would go right through the housing and into the metal of the truck, and could hurt someone. Luckily, trucks are sort of self-protected. But what they did was he took a two by four, and they made or a couple 2x4s, and they made sort of a field goal. So they had these little arms that stuck up, and they had a 2x4 this way, and then they had a long shaft of a 2x4. And the construction worker just came out, took the wire and propped it up like that and nailed it to a tree. And that kept the wire a little higher than it normally would be. And then a couple of days later, I rode by and saw it raining. And all I could think is, God, if someone just walked by and touched that 2x4 with that rain on it, it would certainly zap the crap out of them. It could actually kill them maybe, but it would definitely, they would know they'd been hit. So anyways, keep that in mind. If you ever see power lines down, stay away. Okay. Anybody have any questions on that? All right. Well, there's one last thing that I wanted to discuss with you on here. And I do recommend going back in chapter 8, for instance, and reading Giancolli's discussion. Giancolli, for instance, talks about how to make a galvanometer. That's a very neat, interesting mechanical thing that you can do just by understanding how magnetism works, and where you find magnetic fields, and what causes magnetic fields, and what can make a magnetic field stronger. But it also talks about AC and DC motors, and specifically the DC motor is the part I like the best. But definitely read those little sections and try to work it out in your head what he's talking about how it works and stuff. That's very helpful. There's a section on an alternator for a car that is basically the rudiments of how all electric motors work. And you can actually there's a huge niche for you to work in if you're ever interested. People are always looking for people to repair their washing machine or their dryer, which almost always is just an electric motor. Same thing with a golf cart. A golf cart's an electric motor, and not a lot of people work on them, and they're actually surprisingly simple. Well, simple in the sense of understanding, but trying to get one open and get to an individual bunch of wires that happen to melt, that's a whole different story. But what happens basically in electricity, when you have like an AC or a DC, especially a DC power source, coming into coming into a motor, what happens is the motor basically works on the principle of a current coming through a coil of wires. That coil of wires creates a magnetic field. That magnetic field is compelled to rotate the coil of wires in some particular direction. So for instance, if a magnetic field is pointing up this way, and the south end of a magnet is right here, that means this coil is going to tend to rotate this way naturally, right? Now, as it does that, that's going to actually provide some resistance, because we know that Faraday's law and Lenz's law is going to kick in, and you're actually going to get a back EMF, and that back EMF is going to be something like almost acting like a battery fighting the battery that's running it. So a DC power supply, maybe it's using 12 volts, but now all of a sudden, because it's spinning so fast through this magnet, it's got a huge back EMF that acts like, instead of it having 12 volts, it's like a 12-volt battery put in opposite of a 6-volt battery. Now, here's the problem. If you, for instance, take your washing machine and you do what, for instance, I do when I try to help my wife, is occasionally I might, do some laundry. Well, I'm not a smart man, and I'm also sort of a smart man. So sometimes I choose to put the like all of our bed linens that we have in the house all in the washing machine at one time. And when I do that, that evidently is a little too much weight. You're not really just supposed to pack a washing machine with however much crap you can fit in it. So if that happens, what will happen when the electric motor tries to rotate it is the electric motor is going to try to rotate the actual tub, And normally it would have the tub spinning really fast, and that high speed would have that back EMF slowing it down, and therefore keeping the current going through the wires of the motor very low. But if I put so many clothes in there that it gets stuck, you don't get the back EMF at all. And rapidly the current continues to increase and try to make the spin go faster and faster and faster, because it's got no natural reason to slow down. And that actually causes a current way higher than the motor was intended to use. And therefore you literally just burn out the engine. It'll be basically, if you're lucky, there'll be no fire, but most cases it would be several of the wires would actually get so hot that they melt through the housing and then start touching other wires and all sorts of stuff. But at that point, the motor's shot. So just keep that in mind. But it's very good and very interesting and helpful stuff to understand. You'd be surprised with a little knowledge of physics how much stuff you can fix around the house. So if you don't like doing that kind of work, don't learn it, because you will find a way to do it, or your wife or husband or significant other might find a way to. So let's go to the more general form of Faraday's law. So Faraday's law, the way we've learned it at least, has been basically an induced EMF is equal to negative N d phi sub B dt. Well, we learned that basically we could say delta V, which would be V final minus V initial, which could also be, say, VB minus VA, assuming you're going from A to B, in other words. That's equal to the negative line integral from position A to position B of E dot DL. Okay, we learned that. Now, there was a whole litany of things that came out of that. I taught you that mathematically, once you find a field is conservative, and the electric field generally is, as is the gravitational field, when you find it's conservative, then that implies a bunch of other things that have to be true. So for instance, the definition of, or one of the definitions of conservative, is that del cross E is equal to 0. And in a way that it's not just 0 for a certain X, Y, and Z, it's just naturally 0. Once that's true, then you know this voltage right here, and I'm going to say, put a question mark under it. Actually, I don't want to do it. I'm going to do it in red, because I don't want you thinking this later is right. This is equal to VB minus VA, which I said over there, but it's no longer true in this case, because it turns out that this particular side of it is not an electrostatic situation. So it turns out the electric and magnetic fields are only conservative if they're electrostatic. And the fact that you can have a changing magnetic field means that that line integral from A to V is not necessarily going to be the difference of two scalars that's independent of path. Okay, so no more is that necessarily true. And in fact, Faraday's law in general form becomes the integral of E dot DL is equal to negative N d phi B over dt. And the fact that that left-hand side is not 0 is sort of proof that those 5 or 6 things that I told you that were all equivalent, which meant if you show one is true, then you can already assume that all the other ones are true. That's not the case with this scenario. Okay. Now, with that in mind, let's look at an example. We're going to imagine a very large, so I'll write this in red so we'll see it's an example. Changing B field causes an E field. So what we're going to do here is we're going to imagine a big magnet. Okay. And in fact, this side is going to be the south pole of a magnet. And then very, very close to it will be another big, big, big magnet. And this side is going to be the north pole of that magnet. And in fact, we're going to have a series of very strong magnetic field lines in here. And remember, the rule that I said was that magnetic field lines are like old people. They leave the north and go into the south. So that's the way they're going to point there. You can see when I drew it that it's actually showing the direction. I just made it really small so we'd understand what we're looking at. Now, if I take and look at this from another view, let's say from this view, you might not have known it, but I have green eyes, obviously. Okay, so if I look down from this end, what we're going to see is in fact a large circle. Actually, I don't like that at all. I'm going to use my tools. Yeah, that's perfect circle. Look how good of a circle I made there. Okay, we're going to have this circle. It's supposed to be blue. Why is it not drawn blue? Okay, now it's being a jerk. Okay, now I gotta take it off that automatic draw thing because it doesn't do good when they're on that. So we have a bunch of little magnetic field lines making essentially what's supposed to be a uniform magnetic field sticking out of the page. That's why I'm drawing it. Looks like the ends of heads of arrows. That's the way we indicate that it's sticking out of the page. And we're going to assume basically that the magnetic field is essentially zero outside of this. And we'll say that this radius right here is R0. And we're going to say B equals 0 for R greater than R0. Okay. So now what I'm going to tell you is that there's a current that is creating these electromagnets and therefore the magnetic field. And we can alter that current in time. And because of that, we're going to find that the magnetic field changes in time by dB over dt. Okay, so in other words, that's something we're pretending like we're knowing. It'd be some number of Teslas per second or something like that. And it's basically just a quantity we could use. It could be a function of time. It could be a function of space. I don't know, but it's probably just going to be a function of time for this particular example. Now, what I'm going to do is I'm going to realize that this equation that I just wrote for Faraday's law, the integral of E dot dl over a closed path, and actually I left that off there, over a closed path is actually equal to negative n d phi b over dt. I think if you look at that, you might recognize that it looks a little bit like this equation. Anybody remember what that equation is?
Ampere's law.
Yeah, that's Ampere's law. And remember how we did Ampere's law? It was sort of like a Gauss's law type thing. We would make a closed loop and we called it an Amperian loop. Well, now we're going to make another sort of Amperian loop that we might wish to call a Faradayan loop. Okay, but that's what I'm going to do to analyze this. So first I'm going to consider the solution. What I want to know is what is the E field being produced. So E equals question mark for all R. Okay, so I'm pretending basically like the origin is the center of that circle. Now I'm going to draw an Amperian loop, and that Amperian / Faradayan loop right here is going to be that. And I'm going to go around in this direction. because that's consistent with the right-hand rule. And this is for solution R less than R0. Okay. I'm going to make, like I did in Gauss's law and like I did with Ampere's law, I'm going to make a hypothesis that E is going to equal some E of R, and meaning the symmetry of this makes me think that the only thing that would make the electric field change would be a different distance away from the center of the magnetic field. And by doing so, I'm going to say it's E of R, and it's going to point in what we call the theta hat direction, which we've learned about before. Remember, theta hat direction is basically the direction of increasing theta in polar coordinates. Okay, so with that, the left-hand side of Faraday's law becomes the closed integral of E dot dl is equal to the integral from theta equals 0 to 2 pi of E of R theta hat dot, and you probably remember that the actual little arc length we use would be R d theta, and then of course that would also point in the theta hat direction because that's what dl is. Dl is supposed to be a tangent vector to the actual path we're following. So that's what happens here. Not only that, the fact that we're doing a line integral means that the argument of the electric field, the R, and the R that's in front of the d theta are actually fixed to a constant. So I pull that out in front and I'll have R times E of R. Just remember that's E of R, like F as a function of X. There's not multiplication going on there. Now the dot product of theta hat dot theta hat, we know that's just going to be 1 times the cosine of 0. So we're just going to get the integral d theta from 0 to 2 pi, which is obviously just going to be 2 pi. So I get 2 pi r times E of R. And that tells me, in fact, that E, based on our original hypothesis, is equal. Well, actually, no, I got to do the other part first. Hold on. I forgot to do the left-hand side. That was not good. I mean, do the right-hand side. So now I'm going to do the right-hand side. Now, we only have one path we're following, so the n doesn't really mean anything in this case. We're just going to say d phi over dt is going to be equal to d by dt of the integral of b dot dA. And specifically, this is going to take place over any surface, if you will, that actually spans the green circle that we drew. So the easiest bet would be taking the flat surface that would obviously form in the same plane as the green circle, because this green circle is basically just horizontal as seen in the left-hand diagram. We would just see it as an infinitely thin narrow green line that goes from the left hand, near the left-hand edge of the magnet to near the right-hand edge of the magnet, halfway in between the North Pole and the South Pole. So when I do this, what I realize is the magnetic field is going to be constant everywhere, and it's going to point in the same direction everywhere. And in fact, it's going to be exactly parallel to the dA vector, which actually points from the north field to the south, from the North Pole towards the South Pole. So ultimately, all I'm going to get is that this is d by dt of B times the area, which I'll just write as A. But the area is not going to change, so I'm just going to write this as A times dB dt. Okay. Now, if I really want to get fancy, I can realize that the area is pi r squared dB dt. Now, left-hand side equals right-hand side. Again, this is for r less than r0, gives me 2 pi r E of R is equal to pi R squared dB dt. Now you can immediately see that the pi will cancel out and that this 2 is going to cancel out with this R completely. So I ultimately can get that the electric field from my original hypothesis, the electric field is going to be, oops, I missed a cancellation. There it is. The electric field is in fact going to be R, oops, wrong color. It's going to be R over 2 times dB dt times theta hat, and that is for R less than R0.
Why is it theta hat?
So if you notice from the parallels that we did before with Ampere's law, because this left-hand side looks just like Ampere's law, we try to choose a path that would have those magnetic field lines acting exactly perpendicular to the path that we're following. So I chose to follow a circular path that's in the same sort of plane, if you will, or actually it's in the perpendicular plane from the magnetic field. So that automatically gave me an electric field going in that direction. I'm basically just using the pure analogy of how I looked at a current. For instance, when a current was coming out of a wire, instead of picturing those blue dots right there that you see on my diagram on the right, instead of picturing them as magnetic field, picture them as currents. And I think you'd realize, and actually I should have drawn the arrows the other way. Maybe that's why. Is that why you're asking me about why I said theta hat?
So we're gonna assume that B is in the K hat direction.
Yeah, B is actually coming out of the page in this diagram right here.
Okay.
That's what those little dots mean. And I actually drew these things backwards. So I don't know how I did that or why I did that, but I did it really well. So yay me. Anyways, I want to take that out just for completeness or correctness. All right. So we're actually going to integrate. Whoa, Nelly. I like that one there. Put that there. Put this there. So we're actually going to integrate this way, this way, this way, and this way. And what we can see is sort of this might be, dang it, stop turning into an eraser. This can be our x-axis. This can be our y-axis. And by the right-hand rule, that means z sticks out. And that also means that theta hat is this way. Right there. Of course, theta hat would be this way here. Theta hat would be this way here. This way here. Exactly what we want, in other words. Does that make sense? A little more anyways. Oh, I think I got really small once, so I shrunk it back down to the normal size. Anyways, y'all have what it's what we're talking about here. So did I answer your question well enough, or do you need something else? All right, I think that we'll take that as it's a yes. Okay, so we now have the electric field just for the region R less than R0. Now, when I go to do the same thing in the next part, because we were asked to find the electric field everywhere, I'm going to use a similar circle, but this time the circle is going to be at R greater than R0, which of course, the one time I don't, the one time I do want it to correct my work, it doesn't. There you go. Okay, so that's this time, this is R, and you can see R is greater than R0 with this one. It's like somebody else come in here. That might have been the person I lost. All right, so with the next part, we got to consider R greater, dang it, R greater than R0. Again, we're going to make the hypothesis that E is equal to some E of R theta hat. And again, we're using the symmetry that we used for Ampere's law, which was the closed integral of B dot dl, was actually created by mu 0 I in such a way that we had to draw a circular path around the current, and the current was sort of pictured like a beam coming out of the page. And if it was coming out of the page, we would stick our thumb in the same direction coming out of the page. Imagine grabbing that beam with our right hand, and in fact, our right fingers would then curl around that beam in the direction of the magnetic field. So we now have a magnetic field pointing out of the page, just like the beam of the current that we had in Ampere's law. So we now expect a electric field to be generated that acts just like our fingers going around that I that we had in Ampere's law. So that's where I get the theta hat in further discussion of the question the student had. And now I'm going to say the left-hand side. Whoops, well, I should continue writing in green at least. The left-hand side is the closed integral of E dot dl, which, as you might suspect, is again the integral of E of R theta hat dotted with R d theta theta hat. And again, this is a line integral or path integral. And the nature of a path integral is you have to make the integrand have some characteristic that shows it's on the line that you're talking about. So the line we're talking about is a line that is a arc of radius r, and of course goes through an entire angle from theta equals 0 to theta equals 2 pi. So because of that, that arc means that the r in r d theta, which comes from s equals r times theta from trigonometry, that r is a constant. And since we think E only depends on r, that E of r is a constant. So again, I get r E of r times the integral d theta from theta equals 0 to 2 pi. So finally, I don't know what made me think of that, but I said from 0 to 2 pi. So 2 pi r. I don't know why. There's something wrong with me. All right. So 2 pi r times E of r. Any questions on that? Again, this is just like Ampere's law, which was in some sense just like Gauss's law. So the thing to remember here, guys, is what we learned with Gauss's law is that when we're using Gauss's law specifically to find an electric field, which is not necessarily the best way to use Gauss's law, by the way. I mean, it's, in fact, we can do a lot more with it if we solve the differential equation that is the differential form of Gauss's law. So what we're doing here is a highly niche thing that this calculus-based physics knowledge allows us to do. It allows us to extract or solve for the integrand in an equation that's made of an integral. And in order to do that, we have to have certain symmetries available to us. And those symmetries, if they're true, dictate that the left-hand side of Gauss's law is going to be some area times electric field. Or in the case of Ampere's law, the left-hand side is going to be some magnetic field times a length, like 2 pi r. Okay, well, guess what? Here's E dot dl. So this is going to be, instead of a magnetic field times some length, this one's going to be an electric field times some length. I'm showing you the details so that you might understand why they're coming out that way. But you don't need to necessarily think that much about them until you get more of the mathematical tools that make you feel comfortable with doing this stuff. What you do need to retain from them is the idea that, oh, the left-hand side of Gauss's law is going to be a E times an area, and the left-hand side of Ampere's law is going to be a B times an area, and the left-hand side of Faraday's law, at least used this way, is going to be an E times a length. And I said area a second ago with Ampere's law, and I meant B times the length. All right. So now let's look at the right-hand side. Now the right-hand side, this is sort of like that example I worked for you last class where we had that big boxed off area, let's say an area like this. And then up here in this little area right here, we had an area that actually had an electric field, but it was only in that little area. Let's call that one A2 and this one A1, so that the flux over A1 turned out to just be B times A2, right? Well, the same thing's going to happen here, because the right-hand side, which is supposed to be, let's say, magnitude. Actually, I don't want to write that at all. The n d phi dt just becomes, just becomes d phi dt, which is d by dt of the integral of b dot dA. But again, in this case, it's just going to be area, which is pi r0 squared times dB dt. So again, that's what I'm showing you here. The magnetic field only existed out to a radius r0. That's why the area was truncated down to pi r0 squared. What it basically was going on there is we had an integral of 0 over all the area of A1 that excluded A2. And that was 0 times dA. So you got 0, 0, 0 everywhere. And then when you got into the little bit of area A2, which was in this case pi r0 squared, that was just B times it. And then of course I took the derivative of that, and that just gave me the pi r0 squared times dB dt. So now I can say left-hand side equals right-hand side, and I get 2 pi r e of r is equal to pi r0 squared dB dt. Okay. We do get some cancellations here. For instance, you can see that pi cancels out. Woohoo! Okay. Now, going back with our hypothesis, we know that E for this particular case is going to be E of R, which in fact is R0 squared divided by 2R times dB dt times theta hat. And that is for R greater than R0. And we're down to about 2 minutes left. Okay, so we now have this, and in fact, we can graph this as follows. Let's say, okay, so this is going to be my R axis, and this is going to be my E. And I want to draw right here a value, which if you put in R equal to R0, you're going to get basically R0 over 2 times dB dt. So this will be R0 over 2 dB dt. We saw that the graph is actually, or excuse me, that the function is actually linear for R less than 0. So I'm just going to draw a straight line from here to here. And then once you get R greater than R0, it goes like 1 over R. So we say this is proportional to 1 over R. So that's what the electric field magnitude looks like for that particular thing. It actually, when you look in the circle, for instance, let's draw that circle again. Okay, when you look in the circle, what you're going to find is in the middle, the magnetic field is not so strong. You get further out, it's quite a bit stronger. And further still, it's so strong that the lines are quite strong together. Okay. And in all those cases, of course, the electric field lines are going in a counterclockwise direction. Okay. So that's what it looks like. And then when it gets out here, not only is it a lot weaker, it's getting weaker the farther you go away. Any questions on that? All right. Well, the only thing we haven't covered, well, actually, no, we were supposed to start. I was planning on starting into chapter 30, which is on not only mutual inductance, which we'll do very little with, but with inductance in general. And that is sort of the part of electricity and magnetism that allows us to lay our cell phones down on their back on a charger and it just starts charging. Or I, for instance, have a water pick type toothbrush and it just lays in a cradle, nothing plugs it in, but just laying in that cradle, I'm able to charge it from the cradle. And what's going on there is just like these two coils of wire that I showed you. I've got two coils of wire next to each other. One's being driven with power by being plugged into the wall. The other one's just a coil that connects to the battery in the toothbrush. And the coil with the connected to the power supply is actually generating a magnetic field. That magnetic field is going up through the bottom of my toothbrush and penetrating in through the loop in my toothbrush. And that's actually generating a current in my toothbrush that's filling up, charging, if you will, my battery. Okay. So that's what we're going to talk about, is that mutual inductance, which is really just the ratio of the number of turns, the flux, and the current. Any questions on that? Like I said, we'll talk about that, and the one that we spend most time on, by the way, is what we call self-inductance, or just plain inductance. Mutual inductance, there's pretty much like one problem you can solve, and that's the one they do in the example, and that's it. So everybody's free to go. If you have any questions, I'll wait for the last person to leave before I do. Have a good day and a great weekend. Don't forget to work your test. Also, remember, you guys are allowed, I don't mind you working together on the redo of the test. I really, again, I'm trying to tell you, this is a learning moment for you, not just a moment to get you points. I'm really wanting you to take this as a serious moment where y'all can form a study group or whatever, and we start working with, you know, some of the students that help you that are doing maybe a little better than you. And those of you that are doing pretty well, don't think it's just a tax on you to help other people. You'll actually find that it helps you better understand as you try to explain it. I tutored all the way through my undergraduate and graduate career, and I definitely attribute some of my limited skill set to what I learned from tutoring.
You said that
Yeah.
you for redoing the test, where do you want us to turn it in?
If you look on this week's module, there will be something that's called midterm redo under extra credit. And that's where you turn it in. In fact, let me do a stop share real quick, and let me turn to my
I
module.
didn't see it.
It might be one of those stupid things where I put it there, but I accidentally unpublished it. Let me see. And that looks like exactly what I have done. So yes, it'll be right there where it says week 10, March 20 through 26. It's going to be there. You can see right now it's got the extra credit is, actually you can't see because I'm not sharing my screen. I'm just looking at my screen, but basically it's there. I just don't have it. I don't have it published. So it'll be right there at the bottom of that, and I'll put it there. And about 5 minutes after I get offline, I'll turn it on.
Okay.
Sorry about that, John. I heard what sounded like a lady's voice.
Yeah, that was me, Professor.
Okay,
Younger.
go for it, Maya.
I was just wondering about my midterm, when I would be able to make that up.
Yeah, so you got my email. I know you saw that, and I apologize for forgetting what you cleared.
No, that's okay.
I should have one made either tonight or tomorrow. And that'll allow you probably Monday through Friday of next week to take it. Any one of those
Oh, okay.
days you can fit in.
Okay, that's awesome. Thank you.
Okay, thanks, Maya.
Bye-bye.
Anyone else have any questions? Anybody need to see any notes or anything? Remember, I am putting these notes up on my Google Docs, and you all have access to my Google Docs page.
Yesterday was the limit to look at the problems and the answers for the midterm, right?
Yes, 11:59 last night. You might be able to appeal to a fellow classmate to get them if you neglected to do so. But I had it there. I sent an email out on the day of the exam telling y'all that it would come up on Sunday and you wanted to copy it. And then I sent again Monday or Tuesday, and then I sent it again Wednesday. So yeah, hopefully you got it. If you didn't, just find another student that did.
All right. Cause yeah, I totally forgot. So
Yeah,
I-
if you can't find it, let me know. I'll figure out something to do. It's just it's a lot of work for me to set it back up. So I don't want to have to do it unless I really have to.
all right. All right. Thank you.
No problem. You're welcome.
You said you wanted to type out or, show all the answers that were available. You know what I'm saying?
So for instance, if you took screenshots of the actual problem, you can actually show the multiple choice. I definitely need you to show the right answer. And I sort of just haphazardly asked for all the answers to be shown. But if you just copied the questions and you forgot to do the actual answers except for the right ones, that's fine. I'm not going to take off for that. I just really wanted them all on there.
Okay, because I'm not sure if I have all the whole list
Oh,
or
the
every
multiple choice answers. Yeah, that's okay. Don't worry about it.
I know I have the right answer at least.
Yeah, that's not a problem. Like I said, I wanted it for sort of OCD reasons, but it's fine if you don't do that part.
Okay, thank you.
You're welcome.
I just realized something. Would that have included the testing center midterm?
Yes, I had that one open as well. All you had to do is click on it. I was told a student said they clicked on it in the grade book, and of course it made them, I know they opened up their respond as lockdown browser and then went through it, but you did it through the testing center. That didn't have a respond as lockdown, so you just had to click on it in general. Did you not get it? Are you the same student I was just talking to?
It's available. I just don't remember if you said that it was supposed to show the correct answers or not.
It was, but it didn't show. It only showed up until last night at 11:59 p.m.
Okay.
But it showed since Sunday till then. If you can't get it from another student, contact me. I'll help you get it. Like I said, it's a real pain from my end to do it. So it'd be much better if you can get it from another student.
I don't know who else would have done that.
Everybody seems like so far. So I tell you what, I'll just watch your email. I might post it again because it looks like I have at least 2 students that forgot to do so. So just keep it on the email. I'm probably gonna have to repost it. All right.
All right, because
I
I was just fairly certain that no one else except one other person did the testing center midterm.
Oh, right. Yeah. They might not have done it through the testing center. I think I only had 2 students in this class, and I had 3 in another class use the testing center total. So yeah, there's a very small number of students that did the testing center version.
Yeah, pretty sure those are supposed to be different.
See,
cheating and all that.
Yeah, no, actually, this time I actually made them very similar. I changed the orders. There might have been one question that had a couple words different, but it still had the same answer. So you got lucky on that one. You could have cheated if you wanted to. All right. Yeah, just check your email today and tomorrow. I'm probably going to open it back up and you'll know then. Okay.
All right. Thank you.
You're welcome. Anybody else? Christine, did you have another question or anything?
No, I was just gonna say thank you.
You're welcome. Yeah, have a good one. Bye-bye.